lot for the introduction, and also thanks for the invitation. And I would like to talk today about decarbonizing buildings. We have heard already topics in that direction, and I think it nicely builds also on that what had been said. I would like to start with two cities, which are the most livable cities. I had the pleasure to live in both of them. That's Zurich and Vienna. And if we look at these cities, they have both basically the same target. They want to be decarbonized, or we want to reach our climate goals until 2050, and basically reduce greenhouse gas emissions. And if we look at these buildings which are existing there's a lot of historical buildings, and they are responsible for about 40% of the energy consumptions. If you look at also in Switzerland, 60% of the buildings, they are heated with fossil fuels or direct electricity heating, which we would like to, the fossil fuels we would like to phase out. And Switzerland has about 2 million buildings already built, so it's quite a challenging situation if we think about our greenhouse gas goals in the future. What are measures that we would like to implement in order to reach these targets? There are different levels where we have to work on. At building level, we have to increase energy efficiency by refurbishment, integration of renewables. There are also district level measures. We talk about plus energy districts, energy supply concepts so that also buildings can share energy with each other, energy master plans, until the national level, where we are looking into energy transition pathways. So how do we make the right policies basically to also reach these targets in the future? These are the challenges or the measures that should be implemented in order to reach these targets basically. Where can now machine learning help in that regard? We need a lot of data. Data are often not here. We have heard that already before. But machine learning can help, of course, in analyzing this data, and also at the urban scale, where you have then a lot of different kind of data sets, especially there. It can also help in basically structuring the data and finding typical patterns. At the design stage, we can use machine learning approaches to find the optimal efficiency improvement measures, retrofitting, design new buildings, but also existing energy infrastructure. And finally, at the operational side, also for management and control, we can use machine learning, because we can, if we have operational data, we can use that to train models and optimize basically then also the operational until, for example, the concept of digital twins. I would like to show today two examples, how we have used it in the past, and then also give one example where we are working on at the moment and where I would also like to get your input finally. So let's start with analyzing building data with machine learning. If we look at the whole Swiss building stock, there exists 2 million buildings, about 1.5 million single-family, multifamily buildings where we have some data available. But if we would like to find now measures how we should retrofit these buildings, it would mean we have to analyze all of them, which is quite a challenge. So we try to identify what are typical buildings for Switzerland, and basically work then on a clustering approach in order to identify what are typical buildings that represent our building stock in Switzerland. We use different data sets for that. We have also seen that already, the previous speakers, the GVR data available, OpenStreetMap data. There are the StatEnd data, which talk about building types. You have data about climate, and so on. So all kind of different information which you can use in order to find out the situation for your specific building. So now we took these different data sets. We performed first a grouping, where we did in a fully supervised way, basically in only classifying it into different categories, where we considered the climate zone, we considered the building age, because we know from this GVR data for each building when it was built, and what the building type is. That was the first set, and we arrived to these 270 groups, basically. And then we did then in a second approach, then a clustering approach, where we used this K-Medoids algorithm, and took basically 3 features into account, which we first had to calculate because they were not readily available. One was the building floor area. Then we looked into building compactness, so how, if a building is built in a compact way, if it has neighboring buildings and so on, or if it's a freestanding building, basically. And the third one was then the building density, so what is the environment of the building? Does it get a lot of solar radiation or not? And then with this K-Medwitz algorithm, we tried to identify then what are the typical clusters of these buildings based on these categories. And we arrived then about, per building group, we had then about 4 sets. So we arrived at 270 clusters at the end. Now we tried to, we could still not simulate all of them, all these buildings, to identify what is now the energy consumption of these buildings. So we took then for each cluster a sample of which were closest to the mean, which we then analyzed more in detail. So for each cluster, basically these 50 buildings, and that we simulated then with a dynamic building simulation tool in order to identify what is the heating consumption, what would be the cooling consumption, and so on. Yeah, and then you can also use this to upscale it to the total, to the national scale, for example. Now, just to give you some results, you see here now per age class the cooling loads and the heating loads. Heating loads, you see the older buildings have higher heating, cooling loads, more the newer buildings have the highest consumption. And you can then also go one step further, and you can also look into retrofitting options. So now, if you simulate again these typical buildings, what is the potential for retrofitting? And you see here now in red the energy consumption, and the dashed line, what is the improvement option per category for typical refurbishment options, for example, changing windows or insulating the facade. Now, we have it now basically for these age categories. Now, to derive a certain policy out of that, you would need to upscale that to the national scale and to identify, okay, with which of these measures do I reach actually my targets in the future? So we upscaled all these solutions now to the full building stock, looked also at the stock dynamics until 2050, how many buildings will be replaced, demolished, and so on. And I just want to show you one result now, where you have now here a couple of measures. We have a reduction target, so currently our building stock has about 65 terawatt hours consumption, and we would like to reach in the future a reduction of 20 terawatt hours until 2050. What you see now with this blue line here, basically that would mean a full retrofit, so you would reach this target if you retrofit about 40% of the buildings with a retrofitting rate of 1.5. Just for reference, about at the moment we have about 1%. That would mean you have to insulate the whole facade. What you see then in this violet curve here, that's just windows and the roof. So you also see you reach this reduction target by just insulating just the windows and the roof. But what it would mean is that you have to insulate 90% of the building. So you have to significantly increase your retrofitting rate, which is at the moment just 1%. But what this can help, for example, is that policymakers could say, okay, which measure do we have to support in order to reach our climate targets? That was the first point, so that basically you can derive policies out of that. And the second example, which I would like to also show, is how you now, for a specific building, how do you know what measures now to implement, and basically how can you optimize the building energy consumption? And that goes back again to these clustered buildings where we had a lot of data produced. We simulated all of them with the energy consumption. And we had then in a second step, because we only looked at the envelope first, we have this energy hub approach where we can optimize then the consumption basically, where we also change the system at the same time. And the output is that you see here this Pareto front, where you get a cost-optimal solution, you get a CO2 optimal solution, and some points in between. And each of these solutions, you get the costs, the CO2 emissions, and what systems has to be installed, how large these systems have to be, and what envelope retrofitting measure you would need. And you could go specifically now to a certain building and say, okay, these measures you would have to implement, basically. That is the conventional approach, so basically a physics-based, engineering-based approach. Now we try to find out, okay, because it's quite cost-intensive to do all of that, you need a lot of data, you need to simulate all of them. Can we replace that by a machine learning approach? So we used basically those data, what we had from the conventional approach, to train a machine learning model in order to need in the future then a smaller input set, to reduce the runtime, that it's easier to apply, and that you can also scale that so that you not have to simulate each building separately. So how did we do that? We used different climatic input data. So we had this climatic data, different building data, which should act as an input. Then you would run the machine learning model, and then ideally you would get this Pareto front as an output. And that means we need to predict 10 optimal solutions because we have these 10 optimal Pareto front points, 9 retrofit dimensions. We had about 600 residential buildings simulated and 50 climatic regions, so that acted all then basically as an input data to our model. Now we used a machine learning-based surrogate, or came up with this machine learning-based surrogate model where we trained an artificial neural network. And we did that in that way that we had a first submodel to predict the CO2 optimal solution. Then we had a second submodel to predict all the other points. We did that because otherwise we didn't get good results. And so that we could then derive basically the whole Pareto front. Now we had both categorical variables, but also continuous values. So we need regression and classification in both approaches, where you see here now that mapped. And then in the second one, we basically used then the output of the first submodel as an input. And you see here now the structure of this model, where we first predicted basically the costs and the systems, and then we went further into the type of the energy system, the emissions, and finally then the solar thermal and electric storage, until we reached then the full Pareto front. Finally, we got an R-square value from 0.85, which is quite good, and an F1 score of more than 0.71. And if we look at specifically at now the measures in detail, we see, okay, we reached in average this 0.85, but there are certain categories or certain measures where we were not so good in predicting them. And that was specifically, for example, solar thermal and battery storage, also the storage types, just because we also didn't have so much input data. That was one of the points. And also the PV was in some, especially for smaller size roof areas, was also not very good in predicting. Now we applied that also to a case in Geneva, where you see an area here selected, and you could then, with this target of 10 kilograms CO2 in the future, you see then here now the mean emissions that you could reach that for that area, so 9.9, so that it was able to basically come up with measures to predict that. And what, as a result, we saw that wall insulation and replacement of windows for 43% of the buildings was needed for that specific case. So to conclude that, it's near optimal solutions with quite good accuracy. It's easily accessible building data. That's usually that what it's difficult to get, and it's in comparison quite some reduction in computational costs. So for this case, what I just showed you before, it is just 8 minutes compared to 90 days simulation time, so quite some improvement, and it's quite easily scalable. Now, what we would like to do next, and that's now for us the open question, is we are also involved in one of these suite projects, the Suite SWICE, which is not just looking at technical measures, but also looking at the occupant well-being. And you saw a lot of technical measures which I showed you, but the biggest problem is that we also need the people to implement them and people to change their habits. And we would like to now work again with this clustering, because I think it's a good approach to find out the common trends or solutions for the whole building stock, but use maybe then other data to find out, okay, how do we now predict how people could behave? How do we motivate them to change their habits in order to reduce their consumption? And we thought there of 3 different levels. So there's the individual behavior, which can be easily or fast implemented. That's change of habits, resource-saving lifestyle. Then at the building level, which is more costly, that's these technical solutions which I showed. But there are also at neighborhood scale a lot of these efficiency measures. For example, there's a lot of vacancies where just spaces are not used, which could be maybe also integrated in that we use also that space, or that we could densify, which is another way of making it more efficient in the future. So these are categories which we would like to integrate. And for us, the question is then also, can we build on that existing clustering approaches to include these additional features, or do we have to now recluster everything, and what kind of data sources are there available which could act in that, or could help us in that way? So if you have any hints on that, I would be grateful to hear your thoughts about that. And with that, I'm done. Thank you very much for your attention.